We have covered maximum likelihood estimator and maximum a posteriori estimator. So today we will cover the previous lecture. In the previous lecture, there are some missing topics. So we will cover it, 2 or 3 slides in this lecture. Then we will move towards the least square estimator and minimum mean square estimator. And in the last we will study measures of equality of estimators. So like unbiasedness, variance, consistency, the camera lower bound and feature information. So as we have covered all these things, the maximum likelihood and maximum posteriori estimation. Okay, so we also study this slide. Okay, so basic main difference between MLE and MAP, that MLE do not know the periodic distribution like P of X, and it just used it just find the maximization of the likelihood function, and the MAP knows the periodic distribution P of X, so it uses the Bayes theorem. So now let's start with the MAP estimator with the diffusive period. Um, as you study that the this ML estimator is based on the non-Bayesian approach, and the MAP estimator is based on the Bayesian approach. Okay, so when MAP will coincide with ML for a certain period PDF called the diffuse period PDF, means when MAP estimator will meet a ML estimator for a certain period PDF is called diffuse PDF. This can be seen by rewriting the denominator in the Bayes formula with total probability theorem. So you know this is our Bayes theorem, P of X, condition probability of Z and X and P of X and P of Z. So here P of Z is the total probability theorem, like this one. This is total probability theorem, and this as we already know that this is a normalization constant, and it uses the integral of this all numerator, and it is the product of the condition probability and P of X, and this must equal, the integration must equals to unity to normalize the Bayes theorem. So we assume that the P of X, this P of X uh, over certain region of epsilon. Okay, over a certain region of epsilon, and epsilon is just simply the periodic distribution of X to epsilon. Okay, we will just assume that P of X is equal to epsilon. And what is epsilon? Epsilon just we assume that the uniform periodic PDF for a parameter X over a region. Suppose X is located in the small region of epsilon, having a length of 1 upon epsilon, where epsilon is greater than 0 but very small. And so we just replace the P of X epsilon in Bayes theorem, right? And as well as in this equation, in this equation total probability theorem. Okay, so as you can see in the next slide that you have to put 16 and 15 and 15 like this is total probability theorem, and we just replace P of X with the epsilon, and this will equal to epsilon into G of Z, where G is we just any function, just use any function G. You can use any other variable. It just shows that this is a generalized function, generalized normalization value. Okay, just generalize normalization. Okay, so epsilon g of z. Now then put into Bayes formula, which will yield here. This is formula for Bayes theorem, and the condition probability is the same, and P of x is replaced by epsilon, and P of z is replaced by uh, this thing, this variable epsilon P of z, and here epsilon and epsilon cancel each other, and the remaining part is conditional probability divided by the g of z, and we can replace g of z with 1 over c. Okay, as in the previous slide, what is c? C is the same 2 pi variance of variance square. This is like this, is just normalization constant independent of the x, which guarantees that the PDF integrates to unity. So the 2 pi sigma variance and variance naught sigma naught and P of z. So the this sigma naught and variance of z. Now this diffuse PDF is also called the improper PDF, because as epsilon tends to 0, it does not integrate to unity as a proper PDF does. So another name for it is a non-informative PDF, because it carries no information about the parameter, and that is you can say uniform distribution over infinite interval at the limit. Diffuse PDF uh, causes the posterior PDF like this. This is posterior PDF of x variable to be proportional to its likelihood function. This is likelihood function. This is proportional. So posterior PDF is proportional to the likelihood function, and thus the MAP estimator coincides the maximum likelihood estimator, because as you know, the maximum likelihood estimator ML, this maximum likelihood estimator is equals to the likelihood function of z. Okay, so in this way you can see that the map, when map coincide the maximum likelihood function, or is equal to or it meets to the criteria for the maximum likelihood function, then such estimator is called the diffuse period PDF. The Therefore, we can say that the non-Bayesian MLE is, in view of above discussion, nothing but the Bayesian map. Means MLE and MAP estimator are same with complete periodic ignorance. Okay, so as we already study that MLE estimator completely ignore the period P of x, period P of x, and which is reflected by a diffuse period. Means the maximum likelihood estimator completely ignore the period PDF P of x, but we can use the diffuse period, so that if we use the diffuse period, so that we can show that MLE is equal to the same as a map estimator. So MAP, so both are same. Okay, so the MLE is complete MLE is in of our discussion is nothing but the map estimator with complete ignorance reflected by the diffuse figure. Now the sufficient statistics and the likelihood equation. So if the likelihood function of a parameter can be decomposed as 19, suppose the likelihood function uh, we we decompose it in two functions, f1 and f2. So f1 is a function of g of z and g of z comma x. Okay, where g of is any function of z and comma x and f2 of z. Then it is clear that the maximum likelihood estimate of x depends only on function g of z. Okay, so and this called the sufficient statistic rather than on the entire data set z. We just use g of z. Okay, so we just use the sufficient statistic data for the z. um, instead we are use the entire data. We use the just g of z. Okay, the sufficient statistics summarizes the information about x contained in the entire data.